So again, we have a differential equation, equation 43. The trick to solving this differential equation is to define a new variable, theta, which has this relationship to y. This is what the differential for y is. dy is equal to, use the right-hand side of equation 44. There it is. Note the c comes to the other side. There's the constant. And let's see, what about dx? Well, dx is dx by dy, multiplied by dy, here again is dy, dx by dy. If you look back up here, there it is, replace cy in two different places with this form of the expression relating theta and y. Okay, so as a result, let's see, things begin to simplify here. You can show, just using trig identities, so a little simple math problem, you can show that equation 46 reduces to equation 47. So you can write dx in terms of d theta multiplied by this function, sine squared theta over 2, which is equivalent to the sine squared function is 1/2 1 minus cos theta. We might want to use either one of those expressions. Okay, so we're replacing our independent variable y with a new one, theta. And here's how the dependent variable x depends on theta through this differential. Okay, so what you can do is you can integrate this equation. So you integrate with x on one side, you get an x. Integrate with respect to theta on the other side, you get, well, the first term gives you theta. Second term gives you minus sine theta. And of course, we have an integration constant. We'll call that c primed. Okay. Okay, so now let's remember that the particle in this Brachista-Krohn problem, look back to the original figure that I drew, the particle starts at the origin, so x1, y1, that's 0 and 0. So we know that when y is equal to 0, x is equal to 0. But if you look at equation 44, when y is equal to 0, this means theta is equal to 0. Okay? This means theta is equal to 0. Okay? But y is equal to 0 when x is equal to 0. From this equation, y is equal to 0 when theta is equal to 0. Put those two things together, it means that when theta is equal to 0, x is equal to 0. Okay? Well, let's see. Substitute in theta equals 0 and 0. This whole expression would be 0. You would have, oh yeah, but x is supposed to be 0. 0 equals 0 plus c primed. That's telling you c primed is equal to 0. So as a result, we have x is equal to the same expression as equation 48, just dropping the integration constant. And there you go. Now, let's see. What do we know about x and y? This is x, but y, remember, we had back from this equation, cy is equal to 1/2 1 minus cosine of theta. That was how we defined the relationship between y and theta. So we have x depends on theta, y depends on theta. Oh, these are just parametric equations. And this defines a solution for the trajectory of the particle. Okay? What about this constant c that we've been referring to? Well, we can now use the fact that we know not just what the initial point is, but what the final point, x2, y2 is. Okay? So we know that when y is equal to y2, x is equal to x2. So substitute in y equals y2 in equation 450, and that will correspond to some value of theta, because if you know what x is, x equals x2, that will correspond to some value of theta, which we'll call theta 2. solving this equation, this tells us that cos theta 2 is 1 minus 2 times c times y2. And if you solve for theta 2 and substitute into equation 449 with x equals x2, which is what you're supposed to do because of the subscript 2 on theta and y, indicates we're referring to event number or point number 2. Okay, and 449 was this equation. If you do that substitution, this will yield an equation for the constant in terms of x2 and y2. So this is a little exercise you can work through. It's basically just applying a boundary condition to determine an unknown constant in the solution of a first-order differential equation. Okay, and that's as far as we're going to take it, except I'll just say this. It turns out that these parametric equations, okay, these two equations here with c determined from the value of x2 and y2, the position of the second point, it turns out that these are the parametric equations for a particular function that we call a cycloid. And a cycloid is the following. Imagine that you have a wheel here. So here's a circle, imagine that's a wheel, and you start rolling the wheel to the right, okay? And initially you consider a point on the wheel, which is right at the origin, which is right at the bottom of the wheel. As the wheel turns, of course it moves, let's say to the right. As it moves to the right, what happens to that point on the wheel? Well, it will start to turn around the wheel, but the wheel itself is moving forward. If you actually track the position of that point as it moves along, it will trace out a curve which is the cycloid. And the cycloid will look like this. So a point on the wheel, as the wheel rolls along the x-axis, a point on the wheel will trace out this curve here. That is a cycloid. Okay? It has is a function with the same shape, the same equation describing it as these parametric equations 449 and 450. Okay? That's just an extra little interesting bit of information. Now you may think, well, wait a minute. We're talking about a particle sliding along a track. Well, it can't slide along a track that looks like this. It would fall off the track. Well, but if you multiply that by a negative number, you'll get a track which looks like this. Okay? And it's basically the inversion or the upside down and possibly scaled function here. The cycloid function when it's flipped upside down. This will be the shape of the track, which is the answer to the Brachistochrone problem. What is the function describing the shape of a frictionless track, a frictionless surface, such that if I release an object from rest at this point on the origin, it will make it to another point along this track in the least amount of time. Okay, that's the Brachistochrone problem. The important part of this problem is a little bit less the solution to the differential equation, okay, than how to get to the differential equation. The calculus of variations technique with the Euler equation, that was all about determining what the differential equation is, whose solution is the same as the solution to the original problem, which is tell me the function for the shape of the track, of the surface, that will minimize the time for the object to go from point 1 to point 2. Okay, solve this differential equation, you get x as a function of y. That is the answer to the original question. Okay, everything that followed from this point on was just about doing a little bit of variable substitution, and which is the trick for solving the differential equation. So going through the solution to the differential equation, that is secondary to the main thing I want to illustrate in this problem, which is how to use the Euler equation to construct the appropriate differential equation that you then need to solve. Okay, so let's move on now. So here's the original problem, right? We have an integral, and the integrand depends on x, y, and y prime. So I'm going back to x is the independent variable, y is the dependent variable, y is a function of x, and y primed is the derivative dy by dx. Okay? So if you want to minimize or maximize this integral, then you need to construct the Euler equation and then solve it. So what I'm going to do is I'm going to shift notation here. So the independent variable, instead of calling it x, I'm going to call it t. And the dependent variable, instead of calling it y, I'm going to call it x. So that instead of there being a function y of x, we have a function x of t. And the derivative, which used to be dy by dx, or y primed, is now the derivative dx by dt. I'm going to call that x with a dot over it. Okay? So you can kind of think of x as being position, t is time, and x dot is the time derivative of position, so it's velocity. Okay, that's one way you can interpret it. You don't have to interpret it that way, but that's one way you can interpret it. So let's say you are looking for the function x as a function of t, which minimizes this integral. Well, then we have our Euler equation. It's just equation 53 with these substitutions gives us the Euler equation with the appropriate labels now. X here instead of y, x dot instead of y primed, and t instead of x. Okay. Now, where do we go from here? So that's just shifting notation. That's not very interesting. Let's do the following. Let's consider, okay, here's where it gets really kind of crazy. Let's consider a set of n functions. Okay? N functions of t. x1 of t, x2 of t, all the way up to x sub n of t. Okay? And imagine that we have this more general statement of the problem, which is we have an integral, which depends on big F. Big F depends on t, the independent variable. That's what we're integrating with respect to. But now it depends on function x1, function x2, all the way up to function xn. And it also depends, most generally, on the t derivatives, the derivatives with respect to t of x1, so that's x1 dot, likewise x2 dot, all the way up to xn dot. Okay? Now, just to make the notation a little bit more manageable, I'll use this notation here. X sub I just means the collection of all of these functions. X dot sub I means the collection of all of these derivatives of the functions. Okay, now it turns out that if you go through this a derivation very similar to the one we did for the original Euler equation, it turns out that you can show that each one of these functions satisfies its own Euler equation. Here's what the Euler equation looks like. So we have one Euler equation for each value of the index I. For each function x sub I, we have one Euler equation. Okay? So think about what that means if you have n unknown functions. Okay? Then in order to minimize or maximize this integral, you will have n of these equations. So for n unknown functions, you have n equations. I'm not going to go through the proof of that. The proof is very similar to the original proof.